Hey, Oxygen, I've been thinking recently and I think we should break up.
Are you kidding me? I thought things were going so well.
Well, it's not you, it's more me. Well, I guess there's someone else, CO2.
You're joking. You're gonna ditch me for a mitochondrial byproduct? CO2 is trash.
I'm sorry, like you're great and all, but like we're special when we're hanging out in the lots, but CO2's here now and I really want to be with her. I'm sorry. This is goodbye.
Hey ninjas, has this ever happened to you? Well, it's happened to poor Oxygen all the time. Tune in to this episode of X-Phys Ninja and learn a little bit more about gas exchange and see the unfolding love triangle between oxygen, CO2, and hemoglobin. Check it out.
Try to believe, though the going gets rough, that you gotta hang tough to make it. History repeats itself, try and you succeed. Never doubt that you're the one, and you can have your dream. You're the best around, nothing's gonna ever keep you down.
All right, ninjas. To kick off our episode on gas exchange and regulation, I think it's appropriate for us to first discuss the roles of hemoglobin and myoglobin in the body. So I often will abbreviate those as HB and MB. The first thing I'll say is that these are very similar in their nature. They're both proteins that will bind to oxygen. However, there's some differences thereafter. Hemoglobin is only found in the blood circulation, meaning that hemoglobin can travel throughout the body. Myoglobin, however, is only found in skeletal muscle and cardiac muscle. If myoglobin is ever found in the blood, that means there's been some significant damage to those muscle tissues. So myoglobin stays put, hemoglobin circulates throughout the body. First big difference. Second big difference is to conceptually think of hemoglobin as an oxygen transporter then, whereas myoglobin can be thought of as an oxygen storer or piggy bank. Now, to those ends, hemoglobin can bind up to 4 oxygen molecules, whereas myoglobin can only bind a single oxygen molecule. Now, there's lots of hemoglobin within every single red blood cell, about 270 million, provided it's a properly formed and functioning red blood cell. Within skeletal muscle, there's billions of myoglobin. All that's to say, we can transport a lot of oxygen in the blood on hemoglobin, and we can store a lot of oxygen in the muscle tissue on myoglobin. Another cool fact is that hemoglobin is what gives blood its red color. So an interesting conformational or structural change will occur when hemoglobin is binding oxygen molecules to it. In its deoxygenated state, hemoglobin actually reflects light in such a way that it takes on a very dark red or almost purplish color. And if you were to multiply that out across several hundred million red blood cells, what you end up with is deoxygenated blood that has more of a dark red or purple color to it. Hence the reason you often see deoxygenated blood illustrated in a blue or purple color. However, as the oxygen molecules start to bind to hemoglobin proteins, hemoglobin changes its shape, it reflects light differently, and it takes on a brighter red appearance. Again, multiplied out across several hundred million red blood cells, and what you start to see is an oxygenated blood that has a brighter red hue than deoxygenated blood. So anyway, that's just a fun fact for you. Myoglobin, on the other hand, because it can only bind a single oxygen molecule, it doesn't undergo the same magnitude of structural change, so it doesn't tend to reflect light differently like we might see hemoglobin in the blood. Therefore, we don't necessarily see any color changes in myoglobin. All right, and the last thing that's probably most important to mention is that both hemoglobin and myoglobin love oxygen. In fact, I'm going to change out that word for something called affinity. Affinity means that you love something, you're attracted to something. Both hemoglobin and myoglobin have a high affinity for oxygen. However, hemoglobin tends to be a little more fickle with regard to that affinity, meaning that sometimes hemoglobin has a high affinity for oxygen, but other times it doesn't. And I'm going to get into that in more detail when we look at the nuts and bolts of the gas exchange at various levels throughout the body. However, it's worth noting that hemoglobin's a bit fickle in its affinity for oxygen, whereas myoglobin always has a high affinity for oxygen. Myoglobin always wants the oxygen. Hemoglobin, on again, off again. Sometimes it does, sometimes it doesn't. So perhaps that's a little cliffhanger or teaser for you, but you'll understand how that works a little bit more as we dive into the details. So here we go. Alrighty, let's dive into the crux of this entire episode. Oxygen delivery and CO2 removal. So I've tried to replicate some of the slides that you'll see in your Ninja notes. Please check those out and follow along with me. The first side of this equation is how do we get oxygen into our system and then delivered down to the working tissues. In this episode, I'll use muscles as our example of working tissues. So that's where we come over to this slide right here. What I've tried to illustrate is a single alveolus in the lung. Remember, there's a whole lot of those. And there's a tremendous amount of surface area of those alveoli in contact with the blood supply. In this instance, I've drawn a blood capillary. And remember that the membranes for capillary walls and alveoli are very, very thin. So that allows for simple diffusion of molecules across those two barriers. Now, when you take a big breath in, recall that about 21% of the air we breathe in contains oxygen. And when that oxygen gets down to the alveolar level, then we should have more oxygen in the alveolar area than we do in the returning blood. Now, you may recall some of the partial pressures of interest. After we have sent oxygenated blood out to working tissues like muscles, then it comes back in what we call that deoxygenated state. Now, deoxygenated doesn't necessarily mean that there isn't any oxygen that's returning back to the lungs, but there's less oxygen because the muscles have stripped some of that oxygen from the blood. They've used that for mitochondrial respiration, and now we're getting something with less oxygen back. So the fact that there is less oxygen in the returning blood and more oxygen in the alveolar space, that creates a concentration gradient. And whenever you've got more of something on one side of the space than the other, simple diffusion will occur. In this case, those oxygen molecules simply diffuse across those barriers and they'll bind with hemoglobin. Now, as I've mentioned already, every single hemoglobin, when it's fully saturated, can hold up to 4 oxygen molecules. And every single red blood cell has approximately 270 million hemoglobin inside it. So that's a lot of oxygen that a single red blood cell can carry. Most of the oxygen that diffuses into the blood will bind to hemoglobin. And to give you some numbers, let's just say that's about 95%. 5% of the oxygen that makes its way into the blood is simply going to be dissolved in solution. Now that 5%, even though it's small, does have some significance as it relates to regulation of the respiratory system. I'll get into that in a subsequent episode. So we take in a big breath, get in lots of oxygen in the alveoli. We've got this deoxygenated blood coming back to us, lots of hemoglobin ready to accept oxygen, and through simple diffusion, we get that into the blood. Now that we've got oxygen in the blood, we need to send it down to those working tissues. And what I've tried to illustrate here is a muscle. Now notice that this muscle has myoglobin. Remember that myoglobin is a cousin for hemoglobin. Both of them tend to have high affinities, or in other words, they both really like or are attracted to oxygen. However, one key difference is that hemoglobin's affinity for oxygen is a little bit fickle, whereas myoglobin always wants oxygen. So here comes a red blood cell loaded with oxygen on its hemoglobin, and in this working muscle, there's some metabolites that will change hemoglobin's affinity or attraction to oxygen. A key metabolite is going to be CO2. Recall in metabolism that when we're using mitochondrial respiration, some of those various pathways, CO2 will be produced. And CO2 is a powerful trigger that will induce hemoglobin to release its oxygen. In other words, CO2 is a powerful trigger to reduce hemoglobin's affinity or attraction to oxygen. And there's other triggers at this muscular level that will do the same thing. One of those is pH. So as pH drops, hemoglobin's affinity for oxygen drops as well. Remember that a dropping pH means that something is becoming more acidic. And CO2 as a molecule is very acidic. So if CO2 goes up, pH goes down. So it should make sense that those two triggers are aligned. Also, when working muscles are, well, working, temperature will be increased locally in this area. And an increased temperature also reduces hemoglobin's affinity for oxygen and then gets rid of it. And there's a last trigger that I want to point out. This is called 2,3-BPG, or some biochemists would refer to it as 2,3-DPG. If it sounds familiar, we came across something known as 1,3-BPG in glycolysis. Now, 2,3-BPG is different, but I didn't necessarily tell you the whole truth when we went through glycolysis and metabolism. What I mentioned is that when you start with glucose or G6P, it's going to run its course all the way down through pyruvate. But sometimes glycolysis may end abruptly midstream. And 1,3-BPG can get converted to 2,3-BPG. So the takeaway here is that if a muscle is working, it's a safe assumption that glycolysis is also working moderately or perhaps even in overdrive. And if glycolysis is really cranked up, that means we're going to be cranking out a lot of 2,3-BPG as well. And that 2,3-BPG will diffuse from the muscle into the blood circulation and bind to hemoglobin. And when it binds to hemoglobin, that reduces hemoglobin's affinity for oxygen, so oxygen simply unloads. Now, the last little piece that I want to point out in this particular slide here is that if we've got a lot of oxygen in the blood and we don't have much oxygen in the muscles, we have a concentration gradient yet again. More oxygen here, less oxygen there. So once oxygen is actually unloaded from hemoglobin, it's free to diffuse across that concentration gradient, and so it does into the muscles. Remember that myoglobin always has a high affinity for oxygen. It's like gimme, 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 gimme. So as soon as that oxygen crosses through those barriers, it binds to myoglobin, and at that point in time, myoglobin can take it, translocate it into the mitochondria, and we can do something with that via mitochondrial respiration. So, in a nutshell, oxygen delivery is driven by concentration gradients and partial pressures. Up at the lungs, we have lots of oxygen. In the returning deoxygenated blood, there's less oxygen, so via simple diffusion, oxygen will just cross those barriers and bind to hemoglobin. And then once we take that oxygen down to the muscular level, we have a lot of oxygen in our oxygenated blood. less oxygen here in the working muscle, and there's powerful triggers, most notably CO2. When there's lots of CO2 produced by those working muscles, that helps reduce hemoglobin's affinity for oxygen. It unloads it, and then oxygen just diffuses into the muscle across that concentration gradient. Okay, so let's look at the other side of the coin. This is CO2 removal. Once we have unloaded oxygen from the hemoglobin into the working muscle, we now have empty red blood cells, essentially. And because hemoglobin's affinity for oxygen is low, it now has a high affinity or attraction to CO2. Because remember, hemoglobin's fickle, right? It's not great with staying in a long-term relationship. So the good news is this working muscle has produced a lot of CO2. And because there's more CO2 here in the muscle than there is in the blood supply, we have a concentration gradient. And that CO2, through simple diffusion, will cross these barriers into the blood. Now, like our oxygen up at the level of the lungs, 5% of CO2 will simply dissolve into the solution of the blood. And even though that 5% is a small number, it's actually a really important number because we're going to see PCO2 be the primary determinant of our ventilatory regulation. We also see another 5% of our CO2 bind directly to hemoglobin. 5 plus 5 is 10. What happens to the other 90% of CO2? Well, that other 90% actually goes through a chemical transformation. And CO2 plus water will ultimately help us derive something known as HCO3, I call that bicarbonate, and protons, H+. And you can see that conversion in your Ninja notes. Why is it that so much of our CO2 gets converted to bicarbonate and protons? Well, the reason for that is that CO2 is very, very acidic. And if we just threw all of our CO2 into the blood pH would just tank. I mean, it would just drop to rock bottom. And that's not good because we want our blood pH to be as close to neutral as possible. Bicarbonate, on the other hand, is a very basic molecule. As you've learned already, protons are acidic, but by converting CO2 and water into bicarbonate and protons, we're able to create a buffering system. The bicarbonate basic property is buffered out by the proton acidic property, and we have a neutral effect on blood pH essentially. The only thing that CO2 is going to do to drop blood pH is really this 5% of CO2 here and the 5% of CO2 here. The rest of our CO2 will be carried in the form of bicarbonate and protons all the way up to the lungs. So this bicarbonate piece is really, really cool because that's our body's own buffering system to mitigate the harmful effects of this CO2 acidity. So now that we've loaded up our CO2 into the blood, dissolved, bound directly, or converted to bicarbonate and protons, we got to carry that up to the lungs. And once we get up to the lungs, we have more CO2 in its various forms here than we do in this fresh air supply in the alveolus. Concentration gradient. So the CO2 that was bound directly to the hemoglobin or dissolved in the blood solution, just simple diffusion into the lungs. All of this bicarbonate and protons, well, we're going to see the reverse reaction that we saw here. So the bicarbonate and the protons will get converted into CO2 and water, and both of those will diffuse into the alveolus. At this point, we can go and we get rid of that excess CO2 and some water. Referring back to the first episode on the respiratory system, I had you memorize the percentages of oxygen, CO2, water, and so on in inspired air and expired air. Remember that expired air had greater CO2 and water amounts than inspired air. Here it is, folks. It's this bicarbonate and proton conversion back to CO2 and water. That's how we're getting the majority of that CO2 and water in our expired air. And at this point in time, we have a lot more oxygen in the lungs. We've got a bunch of hemoglobin where we've just gotten rid of the CO2, so it's now got a high affinity for oxygen again, and we go back to our oxygen delivery slide here and repeat that process. Before I leave our oxygen delivery and CO2 removal slides, I want to just put a couple concepts on your radar. Those are known as the Bohr effect and the Haldane effect. The Bohr effect speaks to these two slides here on the oxygen delivery and transport side, and Haldane effect speaks to the CO2 removal slides. I'll go into further depth on both of those concepts later on in this episode, but I wanted to speak about them now with these slides behind me so that you can link those concepts to what I've just discussed as well. And before I leave this whole oxygen delivery CO2 removal piece, I've got another ninja point for you here. This one's pretty cool. So this buffering system that we have with bicarbonate and protons can be exaggerated via ergogenic methods. One of those would be ingestion of some substance that is really basic in and of itself. That might include things like antacid tablets. Tums is a good example. Baking soda, the Arm & Hammer white powder baking soda that you might put in your refrigerator to help with odors. Baking soda is another good example of a very basic substance that you could ingest. One that seems to be a little more tolerable for a lot of people is something known as sodium citrate. So this is an ingredient that many people will use in baking. And what I've got here, I don't know if you can see this in the camera here, but it's basically just a white powder. It looks a lot like salt. And it tastes like salt too. It's very basic in its qualities. If you were to dissolve a bunch of this in solution, a good example would be an amount maybe similar to this. Dissolve that in about 32 ounces of liquid, so a very standard like Nalgene sized water bottle, and drink it. Granted, it's going to be a little salty, but if you were to drink that, say 30 minutes before a high intensity type of exercise, what you're going to find is that your blood pH prior to engaging in that exercise is going to rise, because as this basic substance starts to work its way into our digestive system and then via absorption into the blood, pH will come up as a result. Now, how does that factor into all of this? Recall back to the lactate threshold VO2 max episode, and what I talked about is when you're doing higher intensity exercise, you're inevitably going to be cranking through glycolysis, and you're going to produce pyruvate at a rate faster than you can get that pyruvate accepted into the mitochondria. So while the pyruvate is just hanging out in the muscle sarcoplasm, some of it will get converted into lactate and protons. And then we end up trying, in an attempt to preserve the pH of the muscle sarcoplasm, we kick out the lactate and the protons into the blood. One more time, lactate's a friend. I'll invite it to my house for a barbecue any day, but it's the proton that goes with it. That's the thing that causes problems. So in high intensity exercises, we're kicking more acidic protons out into the blood. Those protons will start to gradually drop blood pH. So now that means that when you're working hard, you've got excess protons that are being ejected in the blood, dropping pH. You've got a bunch of CO2 that's getting pumped into the blood, and that's dropping pH. And this whole bicarbonate proton buffer system is doing its best to maintain a somewhat neutral blood pH. Well, if we could throw some extra basic stuff into the blood beforehand, what we could do is we could buy time. We could start with a higher blood pH before it starts gradually becoming more and more acidic during intense exercise. And practically what that means is that you may be able to perform exercise at your quote-unquote red line for just a little bit longer. Now, they've done a lot of studies on bicarbonate ingestion, sodium citrate ingestion, and variants of this, and they've found that it tends to be, there's a sweet spot of exercise performances that would actually stand to benefit from this ergogenic method. And it would be something probably around that 5-ish minute range. But think about it, if you're a runner, that's going to be something probably in the half-mile to mile range. Maybe you're into CrossFit, high-intensity workouts. There's a lot of stuff that fits in that 5-minute bucket. So this is not an ergogenic method that is harmful to your body, although I will say ingesting a bunch of water that's kind of salty is gross and you feel like you're burping a lot. And depending on what type of basic substance you ingest, some people tolerate it better than others. So sodium citrate, like I've got here, it seems to be a lot better tolerated than just straight baking soda or a bunch of antacid tablets. So it's relatively safe so far as we are aware of, and it's not banned at any competitive level, primarily because even though there is an ergogenic benefit that's been documented, it seems to be very limited to the types of performances that would benefit and how well people can even tolerate it. So with that being said, I thought it was a really cool ninja point to share because it ties in with buffering, right? The bicarbonate and proton conversion that we have from CO2 helps buffer our blood pH, but there's other ways to try and help exaggerate that, and this is just one of them. Previously on As the Gas Passes.
This is goodbye oxygen.
Hey, Oxygen, you okay? Well, if you're free, you can go hang out.
Sure.
Sweet.
Aw, isn't that cute? Don't you love a nice happy ending? I hope you enjoyed this episode on gas exchange, and I hope you learned a little bit more about that fickle relationship that hemoglobin has with oxygen and CO2. Check out that next episode on additional factors that would affect the gas exchange and respiratory regulation. Take care, ninjas.